cycle. This cycle is not only for carbohydrate metabolism, rather it is a common metabolic pathway for carbohydrate, protein and lipids. Gluconeogenesis, glycogenesis, hexose monophosphate shunt, HMP shunt, choline lactic acid cycle. Glycolysis. It is the breakdown of glucose or glycogen up to pyruvate or lactate. It is a catabolic process. It is the main pathway of carbohydrate metabolism to generate energy, ATPs. It occurs in the cytosol. It produces ATP, NADH2, and pyruvate. Significance. Glycogen provides energy to the body, especially brain. Among carbohydrate, brain utilizes only glucose as a primary source of energy. It is also the main pathway for the metabolism of other oxoses, fructose, and galactose. It produces pyruvate, which then produces different metabolic intermediates types. There are two types of glycolysis, aerobic and anaerobic glycolysis. Aerobic glycolysis takes place in the presence of oxygen, and product is pyruvate, and NADH2 is produced, which gives 3 ATP through respiratory chain, which works only in the presence of oxygen. Total 10 ATPs are found, 2 ATPs are utilized, and the net gain is 8 ATP. Anaerobic glycolysis takes place in the absence of oxygen, and product is lactate. Respiratory chain stops in the absence of oxygen. Therefore, the NADH2 produced in anaerobic glycolysis cannot give 3 ATP. Instead, it reduces pyruvate to lactate. Total 4 ATPs are formed, 2 ATPs are utilized, and the net gain is 2 ATP. Steps of glycolysis. Rate limiting reactions is the slowest reactions in any metabolic pathway, which determines the overall rate of the other reactions in the pathway. And glycogen is converted to glucose 1 phosphate. Glucose is converted to glucose 6 phosphate. Glucose 6 phosphate is converted to glucose 6 phosphate. Glucose is converted to glucose 6 phosphate in presence of hexokinase or glucokinase. Glucose 6 phosphate is converted to fructose 6 phosphate in presence of glucohexose isomerase. Glucose 6 phosphate is converted to fructose 1,6 bisphosphate phosphofructokinase, and fructose 1,6 bisphosphate is converted to 3 phosphoglycerate in the presence of uh, aldolase, and 3 phosphoglycerate is converted to dihydroxyacetone phosphate, and the enzyme is phosphotriose isomerase. Now, the 3 phosphoglycerate is in the presence of dehydrogenase is converted to 1,3 bisphosphoglycerate, and 1,3 bisphosphoglycerate is converted to 3 phosphoglycerate in presence of phosphoglycerate kinase, and 3 phosphoglycerate kinase is converted to 2 phosphoglycerate in presence of phosphoglycerate mutase, and 2 phosphoglyceric acid is converted to phosphoenol pyruvate, and phosphoenol pyruvate is converted to enol pyruvate, and enol pyruvate converted to pyruvate, and pyruvate then converted to the lactate. Glucokinase is present only in liver. It its activity depends upon the nutrition state of glucose. It becomes active only when sufficient quantity of glucose is present. It has a high km value. It is not an allosteric enzyme. Hexokinase present in liver as well as in other body tissues. Its activity does not depend upon the nutrition status of glucose. It remains active even at low glucose concentration. It has a low km value. It is an allosteric enzyme. Irreversible reactions of glycolysis. Glucose to glucose 6 phosphate catalyzed by hexokinase and glucokinase. For comparison between glucokinase and hexokinase, these reactions control the rate of uh, glucose breakdown. 1 ATP is utilized to produce glucose 6 phosphate to glucose. It is an irreversible reaction. It cannot be reversed by the same enzyme. The reaction can be reversed by glucose 6 phosphate phosphatase, enzymes of gluconeogenesis, fructose 6 phosphate to fructose 1,6 bisphosphate. This is the rate limiting enzyme. It is a rate limiting reaction catalyzed by phosphofructokinase. Again, 1 ATP is utilized to produce phosphate in this reaction. It is also an irreversible reaction. It cannot be reversed by the same enzyme. This reaction can be reversed by fructose 1,6 bisphosphate, enzyme of gluconeogenesis, phosphoenol pyruvate to pyruvate, catalyzed by pyruvate kinase. It is a two-step process, but it is considered one because enol pyruvate is a very unstable compound which immediately converts to pyruvate. one phosphate is released, which is taken up by ADP and becomes ATP. One ATP is produced at the substrate level. It is an irreversible reaction. It cannot be reversed by the same enzyme. This reaction can be reversed by two enzymes, pyruvate carboxylase and pyruvate carboxykinase. That is the enzymes of gluconeogenesis. Some points about some other steps. Out to fructose 1,6 bisphosphate, two ATPs are utilized. One fructose 1,6 bisphosphate, A hexose, substitution to two trioses, 3-phosphoglyceraldehyde and dihydroxyacetone phosphate. After fructose 1,6 bisphosphate splits into above mentioned two trioses by aldolase, the pathway will run twice because dihydroxyacetone phosphate is also converted to 3-phosphoglyceraldehyde. Each of these two above mentioned trioses produces one NADH2, which in anaerobic glycolysis gives 3 ATP through respiratory chain. Therefore, two trioses will produce 2 NADH2, which will give 6 ATP. In anaerobic glycolysis, respiratory chain shut down, and therefore NADH2 will not be able to produce ATP at all. Instead, it will be utilized to reduce pyruvate to lactate. Each of these uh, two above mentioned trioses produces 2 ATP at substrate level. Therefore, two trioses will produce 4 ATP at substrate level. Each of these two, the above mentions trioses produces one pyruvate. Therefore, two trioses will produce two pyruvate. Or we can say that one glucose produces two molecules of pyruvate. 2-phosphoglyceraldehyde to 1,3-bisphosphoglycerate catalyzed by dehydrogenase. Second phosphate is supplied by phosphoric acid instead of ATP. It is released, which reduces NAD to NADH2. In anaerobic condition, NADH2 produces 3 ATP through as respiratory chain. This is the only oxidative step in glycolysis. 1,3-bisphosphoglyceric acid to 3-phosphoglyceric acid catalyzed by phosphoglyceric glycerate kinase. One phosphate is released, which is taken up by ADP and becomes ATP. One ATP is produced at the substrate level, pyruvate to lactate. Significance of this reaction is that in anaerobic condition, the respiratory chain stops. Therefore, the NADH2 produced during the breakdown of 3-phosphoglyceric glyceraldehyde cannot enter respiratory chain and is therefore unable to produce 3 ATP. Instead, this NADH2 reduces pyruvate to lactate and itself becomes NAD. This NAD is reutilized in the reactions of 3-phosphoglyceraldehyde dehydrogenase. Thus, it keeps the pathway running for some time in anaerobic conditions. When anaerobic conditions abate, the respiratory chain becomes active. Lactate is converted back to pyruvate, and the same NAD takes place. Take back the hydrogen and become NADH2, and then gives 3 ATP through respiratory chain oxidative phosphorylations. Substrate level phosphorylations. When an ATP is formed directly by phosphorylations of ADP with PI without entering into the respiratory chain. Thus, this ATP formations and phosphorylations is known as substrate level phosphorylations. ATP calculations. The net gain of ATP is in anaerobic glycolysis. In aerobic glycolysis is higher than anaerobic glycolysis. The reaction is that in anaerobic condition, respiratory chain shuts down and does not accept uh, process protons, electrons, or hydrogen from donors, NADH2. And therefore no ATP will be produced through respiratory chain in anaerobic conditions. In aerobic condition, respiratory chain becomes fully functional and starts producing ATP. In aerobic glycolysis, NADH2 NADH2 are produced when an NADH2 by each trioses. One NADH2 produces 3 ATP. Therefore, 2 NADH2 will produce 6 ATPs. 4 ATPs are produced as substrate level, 2 ATPs by each trioses by phosphoglycerate kinase and pyruvate kinase. 2 ATPs are utilized. 1 ATP is utilized by hexokinase or glucokinase, and 1 ATP is utilized by phosphofructokinase. Net calculations will be 6 ATPs by 2 NADPI2 plus 4 ATP at substrate level is equal to 10 ATPs minus 2 ATPs. Utilized in the first and third step is equal to 8 ATPs. In if glycolysis starts from glycogen, 1 ATP utilized by hexokinase and glucokinase is spared. Hence, only 1 ATP is utilized. In this case, the net ATP gain will be 9 ATP. Anaerobic glycolysis. Two NADH2 are produced. One NADH2 from each molecule since shuts down in anaerobic glycolysis. These NADH2 instead of producing ATP donate its hydrogen to pyruvate and reduces it to lactate. The 6 ATP produced by 2 NADH2 will not be formed. 4 ATPs are produced are at substrate level. 2 ATPs by each triose by phosphoglycerate kinase and pyruvate kinase. 2 ATPs are utilized. 1 ATP is utilized by hexokinase or glucokinase, or 1 ATP is utilized by phosphofructokinase. Net calculations will be 4 ATPs at substrate level. 2 ATP utilized in the first and third reactions is equal to 2 ATP. If glycolysis starts from glycogen, 1 ATP utilized by hexokinase and glucokinase is spared. Hence, only 1 ATP is utilized. In this case, the net ATP gain will be 3 ATPs. Arabic glycolysis from glucose and from glycogen. Total ATP produced in from glucose 10 and from glycogen 10. Total ATP utilized 2 in glucose and 2 from glycogen, 1 from glycogen. Net ATP gain 8 in glycolysis and 9 in uh, glycogen. Anaerobic glycolysis from glucose and from glycogen. Total ATP produced 4 in glucose and 4 in glycogen. ATP utilized 4 in glucose and 4 in glycogen, 1 in glycogen. Net ATP gain 2 in glucose and 3 in glycogen. Glycolysis in RBC. RBC do not have mitochondria and hence no respiratory chain. Therefore, due to this absence of mitochondria in RBC, the end product of glycolysis will always be lactate. In RBC, there is an alternative pathway of glycolysis resulting in the formation of 2,3-bisphosphoglycerate. 1,3-bisphosphoglycerate is converted to 2,3-bisphosphoglycerate, which is then converted to 3-phosphoglyceric acid. In cells other than RBC, 1,3-bisphosphoglycerate is converted directly to 3-phosphoglyceric acid and produces 1 ATP at the substrate level. In RBC, due to the alternative pathway, this 1 ATP at substrate level will not form. Significance of 3 bisphosphoglycerate present only in RBC. It is an important regulator of oxygen binding to hemoglobin. Its convergence is roughly equal to hemoglobin. When 2,3 bisphosphoglycerate binds with oxyhemoglobin, it decreases its affinity for oxygens. Upon oxygenation, 2,3 bisphosphoglycerate is released from deoxy hemoglobin. Absence of 2,3 bisphosphoglycerate greatly increases the affinity of hemoglobin for oxygens. Presence of 2,3 bisphosphoglycerate greatly decreases the affinity of oxygen for hemoglobin for oxygen. This decreased affinity of hemoglobin for oxygens enables hemoglobin to release oxygen deficiency at the partial pressure found in tissues. Thank you very much. रमजान साहब आप शुरू करें.